All right. We're going to go over function operations and function compositions today. This should be something that you guys all have a little bit of familiarity with from Algebra 2. So it shouldn't be brand new, but it's not something that we had a bunch. So probably be a little bit of rust on here. We're looking at function notation a lot. You're going to see that here. I want to just talk about real quick what f plus g and f minus g and fg and f divided by g mean, like, as far as functions go. Just define those real quick. So it's pretty straightforward for the most part. As far as what it says, it is that f plus g of x will just be f of x plus g of x. In the same way that f minus g of x would be f of x minus g of x. Usually fg is usually one of the main ones that we get confused with, especially with something that we see later when it comes down to something we see here, that fg and then f of g don't mean the same thing. These two things mean something different, so you gotta be careful about that. But just think about what in math, when we put two things next to each other, like 3 and x, right? That we're talking about multiplication there. So fg of x would just be f of x times g of x. And then, of course, f over g of x would just be f of x divided by g of x. Okay, so that's what those things mean. Right? And so let's do some of that. So just paying attention here, right? We have a function f, we've got a function g, and we want to do these operations with these functions. Okay? So fg of x, right? That means f of x times g of x. So I want to take function f, which is x minus 1. Since that's all coming down from the same place, I'm going to put it in parentheses. And then function g, which is x squared minus 1. I want to go ahead and put those next to each other, and I want to multiply them, right? So that's what we're being asked to do here, is multiply. Well, of course, to do that, we just FOIL, distribute, whatever you want to call it. So, of course, x times x is x cubed. Then x times negative 1 would be negative x. And then negative 1 times x squared, negative x squared. And then negative 1 times negative 1 would be positive 1. So the only thing left to do there is, there's no like terms or anything to combine, so we just need to reorder it so it's in standard form. And you do normally put this back on the notation, like, so you could say fg of x equals, so in this case, x cubed minus x squared minus x plus 1. So, when you're doing the WebAssign, it won't ask you to type in the notation. The notation will already be there, but you just need to type in the resulting expression. So you guys will be responsible for this. If you guys were here, doing things on paper with me, then I would definitely be saying you need to write this down, the whole thing. It's part of your answer. So this is a good habit to be in. That your answer should look like this, like with the notation and the answer, not just the answer. Of course, g minus f of g minus f of x. So g is x squared minus 1. And then minus f, which is x minus 1. Now, subtraction tends to be a little tricky. I've seen quite a few people making mistakes with this. Remember that, you can think about that subtractions distributing through there. So that would give you x squared minus 1 minus x, and then plus 1, right? Minus 1, minus negative 1. So make sure you have it switched out to a plus 1. And then you want to combine your like terms and get it in standard form. So g minus f of x. So you'd have x squared, then you have the minus x, and then the positive 1 and the negative 1 would cancel each other. So there would be your g minus f of x. There's no addition example. Addition's just really easy, so it shouldn't be a big deal. Any questions on the multiplication or subtraction examples? The division one's by far the most complex of these. Anybody? Psst. Anybody?
Silence usually means no.
Why are you guys making this awkward?
It's only awkward to you, I promise.
All right, so then f over g. So f was what, x minus 1. G was x squared minus 1. So it's a fraction. So we always need to reduce fractions. Definitely not okay to cancel the ones out or something like that, or say, oh, I have an x and an x squared, those will cancel. I can't do any of that stuff, right? It's x minus 1, it's x squared minus 1. Those subtractions there can't be canceled by division. Okay, division will cancel multiplication. So I should be asking myself what multiplies to be x minus 1. What are the factors of x minus 1? We've done this. This is back in section 1.6. Okay, how do we reduce these? Okay, so we need to think about factoring and reducing from there. Okay. The only thing that multiplies to be x minus 1 is 1 and x minus 1. So there's really no factoring here to do on the top. But you should recognize the denominator as a difference of squares. So I get x minus 1 over x minus 1 times x plus 1. Now I can reduce that because that's multiplication that's happening here. Right? X minus 1 times something, though can be divided out. So now those cancel. And since your numerator's gone, right, that means there's a 1 up there. And then we're left with the x plus 1 on the bottom. And again, those 1s can't cancel because that's an addition. Addition does not cancel with division, so it's not okay. All right, so that's as far as we can go with that. So here's your factoring. Okay, you guys definitely will have a problem like that in the homework. Anything on the division side you guys got questions about? I'll just drink my coffee until somebody says something. This is going to be a really weird video. Thank you, Victoria. All right, so domain is a pretty tricky idea, okay? What we were just doing there with the operations is pretty concrete. It says multiply them, we can write it out, we can do the multiplication. It says subtract, we can write it out, we can do the subtraction. It says divide, we can write it out, we can do the subtraction, division. It's all concrete, we can see it, we can do it. Domain is a pretty abstract idea. It's a thinking idea. Okay? There's a lot of thinking that goes on here. It's almost no work. Okay? It's a lot of thinking though. And so with that, we need to think about, like, when we talk about domain, what does that mean, right? It's all about what x values are allowed to be used in the problem, okay? Another way to say that is what x values can we find answers for, okay? Or sometimes a simpler thing is, because a lot of times there tends to be many x values that we can find answers for. What x values can't we find answers for? What x values is the math impossible to do, okay? And that list tends to be shorter and easier to find. And if we say, hey, I can't plug 5 into that, it makes the math go bad, well, I can say, well, my domain is everything but 5. Right? We find the numbers that are excluded from the domain. It's usually a little bit easier to think about. So if we head to our Wayback Machine here and say, well, we talked about all those toolkit functions, all those parent functions, and I had you guys write all those, like draw all those graphs one day of all the different functions, and the next day we went back and talked about their domains and ranges. Okay? Doing that to get a feel for what types of numbers are allowed to go into certain types of problems. Okay? And so when I'm looking at function f, I say, what types of numbers am I allowed to subtract 1 from? Are there any numbers I can't subtract 1 from?
Can you repeat the question?
Are there any numbers I can't subtract 1 from?
I want to say no.
Right. So there are no restrictions on f, right? We can do that for every number. So we could use every number for f. So then we look at g. Are there any restrictions on g? Are there any numbers that we can't square?
No.
Negatives? No, just kidding.
Yeah, we can do everything, right? We can square every number and then take that number, resulting answer, and then subtract 1 from it, right? It's okay to do that. So there's no restrictions on g. So we should be able to plug in any number we want into either f or g. Okay, well, what types of functions have restrictions, right? We can subtract every number by 1. We can square every number, right? What can't we do, right? Well, I can cube every number. I can take the absolute value of every number. I could cube root every number, but I can't square root every number. So one of the functions that had restrictions on it was square root. What types of numbers can't we square root?
Negatives.
Negatives, right? And so, right, if I can't use negatives, then what does that mean that we can use, right? So we've identified the numbers we can't use, and so then that allows us to start talking about the numbers we can use. So our domain, right, all the numbers that aren't negative, all the numbers that are bigger than negatives, which would be 0 and bigger, right? There's our domain for a square root function. That the radicand, whatever this is underneath here, has to be bigger than 0, or 0 or bigger, okay? So if we have a square root, we've got to watch out. That's one of our functions is a square root. We've got to watch out for our domain. Okay. Then we had one other function that had restrictions on its domain. That was the reciprocal function, or the rational function, 1 over x. When does division go bad? When does division become impossible? What number or numbers am I not allowed to divide by?
When the number you're dividing the number the top one by equals 0.
Right. So say it again, Tiger.
When the denominator equals 0.
There you go. Right. When the denominator equals
Okay.
right. So we can't divide by 0, right? 1 divided by 0 does not exist, right? It's not that we are getting 0 as an answer. It's that number does not exist. Okay. So no 0, right? Well, how do we say no 0, right? I can divide by -1, I can divide by -12, I can divide by 30, right? How do I say everything but 0 in regards to domain? So that domain would look like this, right? I can do any negative number I want all the way up to 0. Right, but I can't include 0. And then I can go to the other side of 0 and go for any positive number I want. But I can't use 0, right? So that's how we exclude 0 from the domain, right? So if there's division, we got to watch out because the denominator can't equal 0. It's not that 0 is wrong all the time. It said the denominator can't equal 0. Like if this said x plus 6, what value of x would make the denominator 0? Right? Well, it would be -6. And say, okay, well, I can't use -6 here. Right? And so those would be my exclusions. Everything but -6. Okay. So what's the value that makes that 0, not just 0? 0 is not necessarily the bad number. It's just what makes it equal to 0. Okay. So we have to look at the function, see if the function itself has a restriction on it. And we also have to look at the operation and see if the operation has a restriction on it. Like once it's been done, did it create a restriction by the math that happened? So when we look at f, right, oops, let me group this stuff, sorry. So we looked at f already, right? We said, hey, f's all good. We can do that. We can plug anything we want in there. G's all good. We can plug anything we want in there. Then we look at f times g, right? Did we create a problem when we multiplied them? Well, can I cube every number? Sure. Can I square every number? Sure. Can I take every number times -1? Sure. Can I add 1 to all that stuff? Sure. So these don't have any restrictions, and this doesn't have any restrictions. So that means this doesn't have any restrictions. Okay, so that means we can use everything. So we're allowed to plug in any number we want into the problem. They will all give us answers. Okay? Let me look at the subtraction one. F's all good. G's all good. When I look at their difference, can I square every number and then subtract it from itself? Sure. There's nothing I can't square and then subtract from itself. So all good. All right, I can use any number. Okay. But division's hairy, right? Division can cause trouble, right? So F was all good, G was all good, but when I divide them, and here's a little weird thing, you have to look at the unsimplified version. When I look at the unsimplified version, are there values of x that would make the denominator equal 0? Because if there are, we can't use them. Are there values of x that would make the denominator equal to 0?
-1.
-1. So if we plugged in -1, right? Does the things go bad, right? So if we say, what happens if we plug? If we say f of g, or f divided by g of -1, right? So we get -1 minus 1 would be -2. -1 squared is 1. 1 minus 1 is 0. Ooh, that's bad. Yep, can't use -1. Anything else that we could plug in and make the denominator 0?
I don't think so.
Anything else we can plug in and make the denominator 0?
One.
1, yeah. So 1 minus 1 is 0, and 1 squared minus 1 is also 0. So this 0 doesn't matter. It's this one that's the problem. I can't take 0 and divide it by 0. Okay? So we have two values of x that we can't use. So we have to make sure we exclude them both from our domain. Okay? So how do I say that? How do I write all that? Okay? It may be easier for you guys to turn this into something more concrete at this point, okay? And which would be like a number line. Okay? So if you want to quickly sketch a number line out and say, how do I draw this? So then how can I talk about it? I'm going to throw 0 in there. Okay? So can we use numbers that are less than -1? Could I plug in -3? Will the math work? Can I plug in -3? Can I plug in -5? Can I plug in -20? Yes, I'm at it. So numbers that are less than -1 are fine, right? But we can't use -1. Could we plug in -0.5 or 0 or 0.2, 3/4? Can we plug in numbers like that? Can I plug 0 into this problem and get an answer? No? F of g of 0, or f divided by g of 0. 0 minus 1 is -1. 0 squared minus 1 is -1. -1 divided by -1 is just 1. Got an answer. So can I plug in numbers that are bigger than -1? Like 0? Like 0.2?
Maybe, I'm not for sure.
I mean, you guys said the only numbers that would make the denominator 0 are 1 and -1. Is 0.2 going to make the denominator 0? 0.2 squared minus 1, is that going to be 0?
No.
No. Right? I'm going to get a gross answer, but it's still an answer, right? What we're looking for are things that don't exist, not just are they messy, right? Not is it difficult, Is it that it's impossible? Okay, so numbers that are bigger than -1 are fine, right? But we can't do 1 either, right? But can I put in numbers except 1? Like, what about numbers that are bigger than 1? Like, can I plug 5 in? Can I plug 40 in?
Yes.
Yeah, right? And so, okay, so think about that, right? Look at that, look at the graph, right? It's basically a solid line, except for there's 2 little blips in it, right? And somebody's doing it in the private chat, so you guys can't see it, but they're saying it's every number but 1 and -1, right? Which, what we said, right? Well, how do we turn that into interval notation? Okay. So when we're writing intervals, right, we start on that left side. On that left side, we see that negative arrow, right? So that's my negative infinity. Then it goes all the way up to -1. But I can't include -1, so it has to be parentheses. And as I hit the other side of -1, so negative 0.9999, it's all good again. But that runs all the way up to 1. And it has to stop just short of 1, so at 0.999, positive 0.99. Then as soon as it flips to the other side of 1, so 1.00001, they're all good again, and then it can go forever from there. So I don't think we've seen a triple interval yet. Okay, and you would just have the union symbols between them, just like always. So this is how you would describe every number but -1 and 1 with interval notation. Okay, so it's kind of complex. It's oddly difficult to exclude 2 numbers from every number in interval notation. Okay. You guys have one problem like that I'm asking you guys to try. Or you have a division that you need to try to find the domain of. Is there anything you want to go back over on that? Yes, no?
No.
All right. It's probably one of the, definitely one of the 2 hardest things we're going to do today. So that's operations. Then we're going to go into function composition, a function of a function. So definitely one of the trickier things here is the reading, right? Getting used to the notation of it. So just like I was pointing out earlier, this little circle here, right? It's not a multiplication dot. It does not mean multiplication. Multiplication is when the letters are right next to each other. This means something else, right? So it's how you read this is f of g of x. Okay, that's how you say that. Okay, and then the next one would be g of f of x. But what that means, right, what it's telling you to do is to take f of x, that's what this is equal to, and you're going to plug g of x into it. Good Lord. Okay, so you take g and you put it inside of f. You're taking a function of another function. You're not multiplying, you're not adding, you're putting one inside of the other. Okay, so that's what that notation means. And I'm going to want you guys to be able to read both forms of it. You'll see the problems switch back and forth from like the parentheses notation to the open circle operator notation. Yeah, this doesn't have a name. Okay. And then this one here would be g of f of x. So f would be inside of g. Okay. So getting used to understand what that means, okay, how to read it. First, we're going to evaluate some functions given a table. So just imagine, it said like find f of 2, okay? Or just, that's the x value right there. So I'd say, well, what's x2? What's the f value, right? What's the function's value at 2, right? So that would just be equal to 8, like that. That's all you have to do, okay? Here's 2, the value is 8, okay? We're going to be looking at compositions. So I want to find f of g of 1. So in order to do that, okay, so imagine we were, thinking like order of operations, right? We always start on the inside layer of the parentheses. So to start this problem, we start on the inside. So you're going to say, well, what's g of 1? Okay. So I go over my table. G of 1 is 3. Okay. Well, what do I do with that? Right? Remember, g was inside of f. I'm taking the function of the other function. So I'm going to take the function f of 3. Right? G of 1 is equal to 3. So I'm going to say, well, what's f of 3? So that 3 goes into the next function. So I say, well, what's f of 3? Well, here's 3. F of 3 is also 3. Okay. So again, normally we would write the answer back in the notation. So I'd say f of g of 1 is equal to 3. That's all you got to do in order to use a table to find the value of a function composition. So if I wanted to find g of f of 4, what would be the first thing I would do? I want to find g of f of 4. What's the first thing that I do?
Look at the table to find f of 4.
Okay, so we're going to find f of 4, Grant. Thank you. What's f of 4 equal to, Grant?
1.
Okay. All right, somebody else. What's next? Thanks, Grant. What's next, guys?
Then do you plug the 1 into the x?
Where? Which x?
Where f of 4 was?
You kind of what you're trying to say, Ruthie?
Or to g of x.
There you go. So we're going to plug that 1 into g. Okay, so find g of 1. What's g of 1 equal to, Ruth? What's g of 1 equal to, Ruth?
3.
So you'd say g of f of 4. And it's just a coincidence that they're both 3, like both examples. Doesn't really have anything to do with anything. Anything about using a table you guys want to go back over? Should be pretty easy. You guys can say yes or no at this point. Thanks, Ruth. All right, we're going to use a graph to evaluate, or graphs to evaluate. So make sure you're watching out that here's graph G and here's graph of F. So which one's which? So I want us to do G of F of 2. So G of F of 2. Okay. So in that same way, you start on the inside of the problem. Okay. So I'm going to say, well, what's F of 2 equal to? So remember, it's normally f of x, so we're looking at that inside. So I want to go to where x is equal to 2, which is right here, right? And then I want to go until I find the graph, which is right here, and then that's, what's the y value, right? It's 5. So f of 2 equals 5. And then I take that and plug it into the outer of the two functions, which is g. So I'm going to say then g of 5. And that's equal to, so where's g equal to, or where's x5? X is 5 here. Make sure on the g graph, looks like it's hitting right about 3. So we got another 3. Again, just a coincidence. G of f of 2 equals 3. Okay. I wanted you guys to see the other notation, so the open circle operator notation, and how do you use that. So you have really kind of two choices. One of them is to translate it into the other notation. So you could just say, well, how do I rewrite that so it makes more sense to me? So that'd be f of g of 4. Okay. Or, which it works, right? But I think you got to spend time translating it. It takes time. Okay. Really, the faster way is learn how to read this notation. Okay. So f of g of 4. Any of you guys that were with me last year might recognize this. Okay. I circle that end of it, right? Because the inside is where we're supposed to start, right? We're supposed to start with the inside of it. So I circle the g of 4, and then I tell myself it's going to go back into f. Okay. So what I'm trying to indicate there is I'm going to find g of 4 first, and then whatever I get for that answer, I'm going to plug into f. Do you see how I'm using that circle with the arrow to indicate that? Does that make sense? Start here, put it into the other one. Okay. So I'm going to find g of 4 first. So I'm going to make sure I go to my g graph. Okay, so where's x equal to 4? X is equal to 4 right there. Well, the y value is equal to 0. So I'm going to say 0. Okay. And then I'm going to take that. I'm going to plug it into f. See what that's equal to. So f of 0. Go over to f graph. 0 is right here. Drop that down. Looks like it's hitting at -3. So f of, oops, let me use the other notation. Any questions about using a graph to evaluate a composition? Thanks, Ruth. She's moving slow. All right. To the other side. These need to be x's. I don't know why they're t's. Or they need to all be t's, or all need to be x's. It doesn't matter. They can't be two different variables in there. I'm comparing the functions. We got a function. We got a function. Okay. And we're going to evaluate them just using the function, right? We did a table. We did a graph. Now let's use the functions to evaluate. Same thing, right? We're going to take the inner, find out what that is. Okay, so we're going to find out what f of 3 is. So f of 3. So that'd be 3 squared minus 3. What's 3 squared minus 3?
6.
6. What do we do with that 6?
Plug it in for h of x.
Yeah, plug it in for h of x. Okay, so take h. So I say h of 6 is equal to 3 times 6 plus 2. Three times 6 plus 2 is 18 plus 2 is 20. So h of f of 3 equals 20. Pretty easy peasy. So if I want to do h of f of -1, what's the first thing I need to do?
Find f of -1.
Okay. let's find f of -1. So we get -1 squared minus -1, right? So 1 minus -1, right? 1 plus 1, so that's 2. And then that would go into the outer function. So we could say that'd be then h of so h of 2, so 3 times 2 is 6, plus 2 is 8. 8. So h of f of -1. Okay. There is nothing stopping us from asking you guys like something like what's f of 2, like something like that. F of 2, like a function of itself. Okay, I would just find f of 2, which would be 2 squared minus 2. Which, man, maybe 2 is not a great number then. Gives me the same answer back. I use like 3. So f of 3 would be 3 squared minus 3, which we said was 6, and then I would take that and I'd say f of 6, which would be 6 squared minus 6, which would be 30. So f of 3 would be 30. So it doesn't change anything. If it's a function of itself, we treat it the same way. Okay, so don't get weirded. It sounds really weird, but it's no different mathematically. So. All right, so domain of the composition functions, again, kind of be tricky, like the domain of the division ones. What this deals with, so it's the intersection of the restrictions on the inner function. So when we say inner function, like this, you know, I've been saying that, like this would be the inner part of the problem, right? That would be the inner. So the domain restrictions on the inner function, and then the restrictions on the composition. So it's pretty similar to what we did earlier when we were trying to find the domain of the operations earlier. So what does this word intersection mean? And so what that's all about, so we've talked about unions. When we talk about a union, that's the U symbol. So the intersection symbol is that upside down U. So when you've seen it there, so I'm just letting you know that you actually won't be using it as we do this, but that's the symbol for it. So what an intersection is, probably the easiest way to think about this is with a Venn diagram. Usually we talk about like, I remember when I learned about these things, it was like through Venn diagrams. So there's nobody here today. Let's see. Okay, I got it. So so if I think about the group of all the students, right? So all of you guys in this that are in this my fifth hour, right? So there's Bridget, and then there's Matt, and there's Grant, and then there's Andrew, there's Ruth, like all those students that are in the class. And then I think about all the people that have talked in the last 30 minutes. So there'd be me, and there'd be Grant, and there'd be Ruth. Okay. So the intersection of those two groups would be Grant and Ruth, because they're the only students that have talked in the last half hour. Okay. So think about that. How you would think about what an intersection would be, where the two circles in the Venn diagram meet. Okay. So if I can find the restrictions on one part of the problem and the restrictions on the composition of the problem, and where do those two circles meet? What things are for both of those? Okay, that's what an intersection is. Okay. So I need to look at the trying to find the domain of this function here. So what may make this a little tougher is the notation they gave us. Okay? It may be hard sometimes to realize which one of those is the inner function. So if you translate it instead, so that'd be f of g of x, okay? It's a little bit more obvious in this notation which one the inner one is. But once you know, you know. So when they say the inner function, that means I need to worry about what's going on with g, or where was the g here? It was right there, right? So it's the second part of the composition. So I need to worry about the restrictions on g. So what restrictions are there on g? Well, g is a square root function, right? And we talked about that earlier, that square roots have certain types of values that can't be put into it. So we can't square root negatives. And so I need to worry about what numbers I plug into this, because there's going to be some answers or some inputs that don't work, right? Inputs that don't give me an answer. So what we need to worry about with the square root is the radicand. This piece of the problem is where the issue is. That piece of the problem can't be equal to, or sorry, that piece of the problem can't be less than 0, can't be negative. So I'm saying that it has to be greater than or equal to 0. Okay? Whatever x is, it can't make that whole thing less than 0. Okay? Also, I set that inequality up. I solve it, so subtract 4 over. So I'd say x has to be greater than negative 4, or equal to negative 4. Right? Plug negative 4 in, I get 0. I know the square root of 0. Plug 12 in, I get 16. I know the square root of 16. Plug negative 10 in, I get the square root of negative 6. Can't do that. Got a problem. So x has to be greater than negative 4. Okay? So there's the restrictions on the inner function. Now we need to find the restrictions on the composition, which means I actually have to do the composition. So if you notice what it's asking me to do here, it's asking me to plug g into f. So what I'm going to do is I'm going to take this function, I'm going to put it into f. So it's going to replace that. That x isn't going to be there anymore, it's going to be replaced. So f of g of x is going to be equal to, well, what's f? It's 1 over something minus 2. Okay? So I'm just taking that x away. It's gone. Right? I'm going to replace it with something else. I'm getting rid of it. What's all the other stuff, right? This stuff is still there. Okay? So 1 over something minus 2. Well, what's that something now? Okay? That something is all of this. Make sure your radical stops here. The negative 2 should not be under the radical. Okay? So make sure you're not being sloppy with that. Okay?
Mr. Baker,
Yes.
why did you make the 4 negative?
I don't know.
I just thought it could
Yep.
be negative.
Yep.
Okay.
Thank you. All right. So if there was more I could do here, I would need to do it. Okay. But I can't simplify this because I don't know what the square root of x plus 4 is. And so then I can't take 2 away from it. So if that square root wasn't there, then I would need to combine my 4 and my minus 2, right? And simplify it down. Okay. So if there was more to do, I would need to do it. I can't simplify it anymore, so I'm done. Okay. But just be aware of that if there is simplifying to do, you need to do it. Okay. So now I need to look at this problem and say, are there restrictions on the composition, right? Remember, we found the restrictions on the inner. Now we need to look at the whole problem and say, are there restrictions on this? Well, this problem's a fraction, right, with a variable in the denominator. And so that means that I could have problems. Are there x values that would make this equal to 0, right? And so it seems kind of odd, but what you do is you go searching for those numbers, right? You say, well, can I get x plus 4 minus 2 to be equal 0, right? And if I can find an answer to this, then I got to say, well, I can't use that number, right? If I said, oh, x is 5, well, then I can't use 5, right? Just like you guys saw on the other one where x squared minus 1 was 0, and you said that plugging in 1 or negative 1 would make the bottom 0, so we said, well, okay, we can't use those numbers. So we go looking for the number to say that we can't use it. It's kind of weird. So I'm going to move the 2 over. I'm going to square both sides. And then I'm going to subtract a 4. So we found out that 0 actually makes it equal to 0. Right? Again, just a coincidence, right? 0 isn't necessarily a bad number, but in this case, 0 does make the denominator equal to 0. Right? Because 0 plus 4 is 4, square root of 4 is 2, 2 minus 2 is 0. So x can't be 0. So x has to be bigger than -4, but it can't be 0. Right? So where do these two things meet? Right? What numbers do both of these things? Okay. So again, are you thinking about it, or are you going to draw it to help you see it? Okay. Are you going to keep it up in your head and be abstract about it, or are you going to put it down on the paper to be more concrete about it? Depends on where your brain is, guys. Okay. So if you want to be more concrete, draw a number line. I need to have -4 on there. I need to have a 0 on there. Okay. So from the -4 business, right? So from this business, it says x has to be greater than or equal to -4. That means I would get a closed dot, and then I could be anything that's bigger than -4. But from this business, saying, hey, x can't be 0, so which means at 0, I should have a little open circle. Sorry, that's wrong. Okay, so then how do I write that as an interval notation? Okay. So remember, we always start from left to right. So from the very left side, the first thing I hit is the -4. Then it keeps going until it hits almost 0. So parentheses 0. And then on the other side of 0, it starts again, and it goes forever to the right. Okay, and it could be either of those intervals work. It can be between -4 and 0, or it can be just greater than 0. All of those values work. Okay? I can plug in -2 and I'll get an answer. I can plug in -1, I'll get an answer. I can plug in 5, I'll get an answer. Okay? I can't plug in -5, and I can't plug in 0. Those are values that would make the problem go. Okay? So that's finding the domain of a composition. Okay? Anything there you guys want to talk about?
No.
Thank you. I'm not gonna worry about this one. I already kind of showed you what g of g or f of f looked like. All right, one last thing. I don't need to show you the whole problem here. I just wanted to show you a little bit of this, kind of the start of it. So adding this on here. So f of x is 4x squared plus 1. And then g of x is 3x minus 1. They want us to find f of g of x. Okay. So kind of using that notation I was using earlier, that circle, right? Wants me to take g of x, plug it into f. Okay. So I'm going to take this function, plug it into that function. So I'm going to take f, which is 4 times something squared plus 1. Right? You see how I just pull the x out? I leave a space in there. Okay, but everything else that's around the x is there. Okay, so I kind of create a shell for the problem, right? Just take the x out. Okay, what am I going to put into the x? I'm going to put 3x minus 1 in there. Okay, so there's the structure of it. Here's what I need to do. Now we need to do it, right? The simplifying part of it. I was talking about that earlier, right? If you can simplify, you need to. Well, this is simplifiable, okay, but you got to make sure you do it the right way. Okay, so make sure you're following order of operations. Okay. Look inside your parentheses. There's nothing to do inside the parentheses. Go to the exponent. So how do I deal with the exponent? Okay. So that means I need to square that thing. So squaring means multiplying something by itself. Do not drop the exponent in. And then I need to do that foiling. I would really suggest that you do the foiling first. Don't worry about the 4. You are not allowed to do this with the 4. That is bad math. Okay, you're not allowed to do that. You can do that if you want, but I would suggest that you don't. Okay, I would suggest that you start by doing this. Go ahead and do your FOIL first. So that would give you 4 times 9x squared minus 3x plus 1. Okay, and then you'll just finishing it from there is pretty straightforward. So, okay, I just wanted to again highlight that idea that you have to one, how to plug in the whole function into another. Okay, then you need to square it like this. Okay? You can't just drop the exponent, that's bad. Okay, but the rest of the simplifying should be easy. You guys do have a problem like that, so I want to make sure you saw a part of an example.